Okay, let us start a theorem. Every continuous function is integrable. Every continuous function is integrable. So integrable means I am taking account into this Riemann integral. Okay. So every continuous function is integrable. So now start it. Close. So we shall prove that if f is a function or if f is a continuous function, f is a continuous function on closed AB, then f is integrable on closed AB. Then f is integrable on closed AB. Let us on a closed interval closed AB. If f is continuous on that closed interval, then f is integrable or f is Riemann integrable on that interval. So let epsilon greater than 0 and choose a positive number eta, such that eta whole into b minus a is less than epsilon. So choose epsilon greater than 0, be arbitrary and choose a positive number eta such that eta whole into b minus a, this thing is less than epsilon. And here it is given that f is a continuous function on closed AB. Since f is a continuous function on closed AB, so we have a theorem that says that if f is continuous on closed AB, then f is bounded on closed AB and f is uniformly continuous. This is uniformly continuous on closed AB. So this is a theorem. If f is continuous on closed AB, then f is bounded. Continuous means its value already exists. That means in between a and b, if you put any values in place of x, then f of x exists. So that's why since exist means it gives some finite value, that means f is bounded and also f is uniformly continuous. It is a theorem, just I am using that theorem only. So if f is continuous on closed AB, so since f is uniformly continuous on closed AB, then we can say, or which implies there exists delta greater than 0 such that f of t1 minus f of t2 modulus, this thing is less than eta for t1 minus t2 modulus less than delta, where t1 comma t2 belongs to closed AB. This is the definition of uniformly continuous of f on closed AB. That means since f is uniformly continuous on closed AB, then we can say that there exists a delta greater than 0 such that f of t1 minus t2 modulus is less than eta for t1 minus t2 modulus less than delta, where this t1 t2 belongs to closed AB. That means f is uniformly continuous on closed AB. That means if you will take the distance between any 2 points, this thing is very close to less than delta, means delta is a very small positive number. This thing is less than delta means if t1 is very close to each other, t1 and t2 are very close to each other, then its functional value is also very close to each other. This is the meaning of your uniformly continuous. on closed AB of f. So since it is uniformly continuous, then we can conclude these things. So now we can choose a partition. Now we can choose a partition P which is equal to x0 which is equal to a, then x1 x2 dot dot xn which is equal to b. Then we can choose a partition P such that norm P is less than delta. Let this is where equation 1 with such that norm P is less than delta. Then equation 1 becomes then from equation 1 we have, so what can you say from the equation 1? Where this t1 t2 are any 2 points from closed AB and their functional value modulus is less than eta. That means we can say capital Mi minus small mi modulus, or capital Mi, since capital Mi is always greater than or equal to small mi, its modulus means simply this is capital Mi minus small mi. So this thing is less than eta, less than equal to eta, because t1 and t2 are any 2 points in from this closed interval AB, and among this closed interval AB, so if I will choose a particular, so among this closed interval AB, if I will choose any particular subinterval, this is your ith subinterval xi minus 1 to xi. So if I will choose this ith subinterval, and if I will choose the maximum point or the supremum of f of x in this ith subinterval, suppose this is your capital Mi and small mi is the infimum value of f in this ith subinterval. So if you will take the difference of capital Mi and small mi, so this thing must be less than equal to your eta. So this thing is less than eta for any of the intervals, any of the subintervals I equal to 1 2 3 dot dot up to n. So now if I will consider my UPF minus SPF, consider UPF minus LPF. So here UPF minus LPF, that means this is just summation of I from 1 to n capital Mi minus small mi into del xi. So capital Mi minus small mi, this thing in place of this one, I can write this thing is less than equal to eta. Then it can go to the outside of this summation because it is independent of I, because the summation is over I. This is I from 1 to n, this is del xi. And what is the summation of del xi? This is equal to eta whole into b minus a, because the summation of I from 1 to n your del xi, this is your b minus a. So this is eta whole into b minus a, and I have chosen from the starting, we just choose that eta in such a way that eta whole into b minus a is less than epsilon, because this thing will come. That's why we choose our delta, we choose our eta accordingly. So this thing is less than epsilon because this is the choice of our eta. So what we got here, UPF minus LPF, this thing is less than epsilon, thus f is integrable. That means if f is a continuous function, then f is integrable. So if I will repeat this thing, every continuous function is integrable. That means suppose f is any continuous function on closed AB, then f is integrable on closed AB. So let epsilon be any arbitrary small positive number, or epsilon greater than 0 be arbitrary. Then choose a positive number eta such that eta whole into b minus a is less than epsilon. And here given that f is continuous on close AB, so when f is continuous on close AB, then we can say that f is bounded on close AB and f is uniformly continuous on close AB. So which implies that there exists delta greater than 0. So f is uniformly continuous. That means this is the this thing we can write. So f is uniformly continuous on closed AB, which implies that there exists delta greater than 0 such that f of t1 minus f of t2 modulus is less than eta for t1 minus t2 less than delta for all t1 t2 belongs to closed AB. Since it is uniformly continuous on closed AB, so if t1 t2 points are very close to each other, then its functional value is also very close to each other. That is the concept of uniformly convergence of f. So if this thing happens, so if f is uniformly continuous, then this thing happens. So now we can say, or now we can choose our partition P consisting of points a equal to x naught, x1, x2 dot xn equal to b such that norm P is less than delta. Then from equation 1 we have, since f of t1 minus t2 is less than eta where t1 t2 are any 2 points of closed AB. So if I will choose any point from closed AB, suppose if I will choose a subinterval xi minus 1 to xi, and we know the supreme value of f in this subinterval is capital Mi and infimum value of f is small mi. So if in particular I will choose the difference of capital Mi minus small mi, so we can say this thing is less than equal to delta or strictly less than delta also we can say, because this for any t1 t2 belongs to close AB. So this capital Mi minus small mi is less than equal to delta for I equal to 1 2 3 dot n. So now if I will consider what is my UPF minus LPF, and you know UPF minus LPF can be written as in this way. This is summation of I from 1 to n capital Mi minus small mi del xi, because your UPF is summation of I from 1 to n capital Mi del xi, and your LPF is summation of I from 1 to n small mi del xi. So and this is the difference of these two. So this thing is less than equal to epsilon, less than equal to eta, because this capital Mi minus small mi is less than equal to eta. So since I will put this eta, so accordingly I will use this inequality less than equal to eta, and also it can go outside this summation. So this will be eta into summation of I from 1 to n del xi, and summation of del xi, this is your b minus a. So this is your eta whole into b minus a, and eta whole into b minus a. This thing is less than epsilon. So UPF minus LPF is less than epsilon, thus f is integrable. So it is proved. Now come to the next theorem. So the next theorem is, if f is a monotonic on closed AB, then it is integrable on closed AB. Then the next theorem is, if f is monotonic on closed AB, if f is monotonic on closed AB, then f is integrable on closed AB. Integrable on closed AB. So we already know that given that f is monotonic, on closed AB, monotonic on closed AB, we have to show that f is integrable. That means we have to show that UPF minus LPF is less than epsilon. So if f is monotonic on closed AB, what do we mean by monotonic? So f is monotonic on closed AB. That means monotonic means there are two types of monotonic. That means monotonic increasing or monotonic decreasing. That means we can say that f is monotonic increasing, f is monotonic increasing, or f is monotonic decreasing. F is monotonic CREASING. F is monotonic increasing or monotonic decreasing on closed AB. Suppose you can assume anything. If it is monotonic increasing, then do something, or if it is monotonic decreasing, then do something, and then conclude that f is integrable. So but now I will consider only these things. Suppose it is monotonic increasing, then how I will conclude that f is integrable. Also similarly you can do for monotonic decreasing, or you can take anything and just conclude your theorem. So I will consider this thing. Suppose f is monotonic increasing and close AB. Suppose f is monotonic increasing. Suppose f is monotonic increasing and close AB. So f is monotonic increasing means if you will gradually increase the value of x from close AB, then its functional value is also gradually increasing. So gradually increasing means its function value exists. So we can say its functional value exists for all x belongs to closed AB. That means f is bounded, because we are getting a finite value, means we can say f is bounded. So suppose f is monotonic increasing and closed AB, then f is bounded on closed AB because its value exists. Then we are comparing it is monotonic increasing things. So f is bounded on closed AB. Now let epsilon greater than 0 be arbitrary and choose delta greater than 0. Choose eta greater than 0. So here also we will choose an eta. So what is the condition on eta? Choose eta greater than 0 such that eta divided by f of b minus f of a plus 1, this thing is less than epsilon. And after some steps you will see why I choose my eta in this way, or the conditions on eta why I choose in this way. Because I have to get less than epsilon on the last step. That's why I have chosen this thing in this way. So epsilon be any, or epsilon is arbitrary. Choose eta greater than 0 such that this thing is less than epsilon. So we now choose a partition P. We now choose a partition P having points x0, x1, x2 dot dot xn equal to b such that mu p is less than delta. Now since f is monotonic increasing on closed AB, since this thing is monotonic increasing on closed AB, so f is monotonic. So this thing is also monotonic on any of its subinterval. Suppose this is the ith subinterval. So f is monotonic increasing on ith subinterval also. So in ith subinterval we know capital Mi is the supremum of f of x for x belongs to this subinterval, and small mi is the infimum of f of x for x belongs to this subinterval. And since I am saying it is monotonic increasing, so small mi must be your f of x I minus 1. That means gradually, when I will gradually increase my x, then the corresponding f value increases, or corresponding functional value increases. So small mi means this is f of at the initial point x I minus 1. Similarly capital mi means this is functional value at the end point or terminal point. This is the functional value at the initial point. This is your small mi, this is your capital Mi, since f is monotonic increasing on this closed interval. So this is your capital Mi and small mi. So for I equal to 1, 2, 3 dot dot up to n. So now if I will consider, so now consider my QPF minus LPF. So what will be it? This is the summation of I from 1 to n capital Mi minus small mi whole into del xi. So capital Mi minus small mi. So in that place I can write this thing. This is just I from 1 to n. This is your capital f of xi minus f of xi minus f of xi minus 1 whole into del xi. Then what is f of xi minus f of xi minus 1? This is your this one, and we have del xi. So in place of del xi we can replace one thing. Del xi means this is the ith sub interval, and we have chosen this mu p. This thing is less than delta, and also we have chosen another thing for epsilon greater than 0. This is your eta. So I just want make one thing change. So here choosing the partition P, we choose the partition P, which is your a equal to x naught, x1, x2 up to xn, such that mu p is less than eta. Okay, this is the eta. No delta is there, and this is this eta. So this eta will satisfy this thing. That means norm of p is less than eta. That means whatever the subintervals you have in closed AB, the maximal subinterval length, this thing is less than eta. So if I will put the maximal subinterval length here, then I will give the less than symbol, because this is the less than symbol here. So less than eta. Then this is summation of I from 1 to n. This is your f of xi minus f of xi minus 1. Okay. So this thing, remember, whatever the eta we have chosen, this is the norm of that partition. Or norm of that partition is less than that number eta. So in place of del xi, I will put this thing. This is eta. That's why I have given the less than symbol. Then this thing is less than this one. So if I will add this thing f of xi minus f of xi minus 1 from 1 to n, so this thing will be your f of b minus f of a. So this thing is equal to, that means if I will expand this thing, this is your f of, if I will put in place of I equal to 1, then this is f of x1 minus f of x0. Similarly, f of x2 minus f of x1. Similarly, for n, f of xn minus f of xn minus 1. So if I will cancel the terms, whichever are cancelling, then f of x1 minus f of x1, similarly f of x2, then f of xn minus 1. So only things left are eta whole into, this is f of xn minus f of x0. So which is your eta whole into f of b minus f of a. So if this is your these things, so if I will put the values of eta, here we have here the condition on eta is this one. This is your f eta divided by f of b minus f of a plus 1. This thing is less than eta. So this implies, if I will write eta on one side, so sorry, there is also this thing. So you are choosing eta in such a way that eta is less than equal to so here we are choosing eta such that eta is less than equal to epsilon divided by f of b minus f of a plus 1. Okay, you will remember this thing. So in place of eta I can write this thing is less than epsilon divided by f of b minus f of a plus 1, and this is here f of b minus f of a. So since this is a positive quantity f of b minus f of a, and this is f of b minus f of a plus 1, so this thing is the numerator is smaller than denominator, so obviously this thing will be less than 1. That means I can say this is less than equal to epsilon into 1. That means this thing is less than epsilon. That means here UPF minus LPF, this thing is less than epsilon. Thus f is integrable. Thus f is integrable. So now see it again. So if f is monotonic increasing, so if f is monotonic and clojure, then it is integrable, we have to show. So f is monotonic means either monotonic increasing or monotonic decreasing. Suppose I will consider for monotonic increasing, then I will show that f is integrable. So suppose f is whether it is monotonic increasing or decreasing, then you can say f is bounded, because f value exists, that's why we are comparing with other things. So f is bounded because its value is finite. So f is bounded, then choose your epsilon greater than 0 be arbitrary and choose eta greater than 0 such that eta is less than epsilon divided by f of b minus f of a plus 1. Okay, this thing if you will forget this relation, what is the condition on eta, then you will go to your last step. If you will see your last step is this one, and you have to show this thing is less than epsilon. This thing will be less than epsilon. That's why you will put in place of eta epsilon divided by f of b minus f of a plus epsilon. So if you do not remember what is the restriction on eta, so when you will come to this step, this step, then you will automatically get back what is the condition on eta. So your condition on eta is less than epsilon divided by f of b minus f of a plus 1. Okay, so if you will put the condition of eta, then it will be less than epsilon divided by f of b minus f of a plus 1, and your right hand side is this one, f of b minus f of a, and you know f of b minus f of a divided by f of b minus f of a plus 1. So this thing is less than 1 because this thing is smaller than this one. So smaller divided by larger means this ratio is less than 1. So this is epsilon, this is less than equal to less than of epsilon into this ratio is 1. So your UPF minus LPF is less than epsilon, thus f is integrable. So these are the two theorems. Then come to a note. So what in the above two theorems we get? So if f is continuous, so what we got from the above two theorems, if if f is continuous, then it is differentiable. If f is continuous, then it is differentiable. That means it is if it is continuous, then it is integrable. Then it is integrable. And in second theorem, if f is monotonic, then f is integrable. Also there are some more statements, so I will say only the statement. If f is a bounded function, if f is a bounded function and it has only a finite number of points of discontinuities, it has only a finite number of points of discontinuities, finite number of points of discontinuities, then finite number of points of discontinuities on closed AB, then f is integrable on closed AB. Integrable on closed AB. And also there is another statement. If f is bounded on closed AB, if f is bounded on closed AB, bounded on closed AB, but it has a set of infinite, it has infinite points of discontinuities, but it has infinite points of discontinuities, infinite points of discontinuities, if f is bounded on closed AB, but it has infinite points of discontinuities having finite limit points, having finite limit points, then f is integrable on closed AB. So these are about the functions f such that f is integrable. So the first one is saying if f is continuous, then it is integrable. We already proved this thing. So and the second one is saying if f is a monotonic function, then it is integrable, and already also we proved that thing. And the third one is saying if f is a bounded function and it has only a finite number of points of discontinuities. The first one said to you that if f is continuous on closed AB, if f is continuous on closed AB, then f is integrable on closed AB. That means if it is continuous at every point of closed AB, then it is integrable on that interval. But the third one is saying f is bounded, it's okay, but if it has a finite number of points of discontinuities, that means if it is continuity, I mean everywhere continuous means it is integral, but this one is saying if it has a finite number of discontinuities, that means there are some finite number of points where the function is discontinuous, then also you can say this is integrable. And the fourth one is saying suppose this f has infinite number of points of discontinuities, but what are the points of discontinuities? If we will take their limits, that means if we will collect the points where it is discontinuous, so if we will collect, if we will take their limit and the limits are finite, that means suppose if you will say, suppose S is a set which contains S1, S2, Sn, like this, there are infinite number of points where this f is discontinuous. That means I am taking the points of discontinuities where are the points, this is the set S where f is discontinuous, where f is discontinuous. So there are infinite number of points where f is discontinuous. So if we will find the limit of s, if this is finite means this is suppose 1, 2, 3 for something, whatever it may be, this is a finite quantity, or suppose this thing will some a or b, that means it has a finite number of finite number of limits. It has finite limits and finite number of limits also. You can say finite number of limits, finite number of limit points. That means suppose this is a infinite set, it has finite limit a. Suppose similarly there is S1, it also contains some infinite number of points where f is discontinuous. So, but if you will find its limit, limit of s1, suppose this is b, here limit is equal to a, here limit equal to b. That means if you have infinite sets of discontinuity, but if its limit is finite, or if you are getting only a finite number of limit points, then that function f is integrable. So these are the conditions on f such that f is Riemann integrable. Now, if we will come to a problem, suppose this is a problem. If a function f is defined and closed ab as follows, if a function f defined and closed ab as follows, as defined on -1 to 1, defined on -1 to 1 closed interval as follows, and the defineness of f of x, this is your k. K is a positive constant when x is not equal to 0, and this is 0 when x is equal to 0, and here where k is a positive constant. Okay, so f is here the function f is defined on -1 to 1 closed interval in this way. F of x equal to k is a constant when x is not equal to 0, and this is 0 when x is equal to 0. So if we will see the above four statements are on the continuity. If it has continuous, then it is integrable. If it has suppose it has some discontinuous point, then the number of discontinuous points should be finite. It has finite number of discontinuous points. And the last one is saying if it has infinite discontinuous points, then their limit points should be finite. So these are the all three things about the continuity. So suppose your f of x is equal to this one, and if you will see the continuity of this function f on this closed interval ab, so if we will check, the continuity of f of x on closed interval -1 to 1, we will see that f is discontinuous only at x equal to 0. So if we will put only at x equal to 0 the function is discontinuous. So since the only discontinuous point is this one, or you can say if it has a finite number of discontinuous point, because only 0 is the only discontinuous point, thus we can say that f is integrable, because 0 is the only discontinuous point. So how you will check the discontinuous things? Because at x equal to 0, so if you will see the points of discontinuity, so at x equal to 0, if you will see the points of discontinuity, so how you will check? So first you will find f of 0, this is 0, there is the functional value of, that means you have to check limit of f of x extends to 0, this thing will be equal to its functional value at 0, but f of 0 is 0, but if you will take this thing limit x goes to 0 f of x, so what is this value? So limit, you know how to find a limit x goes to 0 minus you have to calculate, then limit x, left hand limit, right hand limit. So limit x goes to 0 minus f of x, this is how much? Limit x goes to 0 minus, what is your value of f of x when x is 0 minus, that means on the left hand approach of 0, this is k, because only at 0 When x is equal to 0, then f of x equal to 0, otherwise it is k. So when x goes to 0 minus limit of k equal to k. Similarly, if I will calculate limit x goes to 0 plus f of x, this is the same thing, limit x goes to 0 plus at that time your f of x equal to k. So this is independent of x, so the left hand limit, right hand limit equal to k, that means your limiting value equal to k but the functional value equal to 0. That's why this is k, this is 0, and I am saying this k is a non-zero constant, so k is not equal to 0. That means 0 is the only point of discontinuity of this function f. So since 0 is the only point of discontinuity, that means it has a finite number of points of discontinuity. That's why f is integrable. Similarly, if I will go to another example, so that the function f defined as follows. So that the function f defined as follows. Here f of x is defined in this way: 1 by 2 to the power n, when 1 by 2 to the power n plus 1 is less than equal to x is this thing is less than x, which is less than equal to 1 by 2 to the power n, for n is equal to 0, 1, 2, 3 like this, and this thing equal to 0 when x is equal to 0. So if x is equal to 0, then this value of functional value is equal to 0, and when x lies between this interval, then f of x equal to n. And we have to show that the function f is defined as follows, so that f is integrable. So that f is integrable on -1 to 1 closed interval. Okay, so if we will see this problem, so what is your f of x? Yeah, clearly this is 0 when x is equal to 0, and if I will put n is equal to 1, so okay, first I will start for n equal to 0. So if your n is equal to 0, then in place of n I will put 0, so 1 by 2 to the power 0, this is your 1 when x lies between, in place of n you just put 0, then this is 1 by 2, this is 1 by 2 to the power 0 is 1, so 1 by 1 is 1. So when x lies between half to 1, this is 1, and then this is 1 by, so now I will put in place of n 1, so if you will put n equal to 1, then 1 by 2 when x lies between 1 by 2 square to 1 by 2. Similarly, this is 1 by 2 square, in place of n I will put 2, so this is 1 by 2 cube less than x less than 1 by 2 square. So these are the functional values of x. If I will put n, this is for n equal to 0, this is n equal to 1, this is n is equal to 2, and this is for x equal to 0, this thing is 0. So this is the functional values. So if we will notice this thing, here the x lies between -1 to 1, and the functional values is lies between 0 to 1. That means here when x equal to 0, the functional value is 0, and when I am increasing the values of x, when it goes to 1, then the functional value is 1. That means we can say here the f of x is a monotonic increasing sequence. This is a monotonic increasing sequence. F of x is bounded because its value is lying between 0 to 1. Whatever the middle values, these are lying between 0 to 1. So we can say f of x is bounded on 0, 1 and is a monotonic increasing function on -1 to 1. So in between -1 to 1, whatever the x will put or this thing, for that values of x, f is your monotonic increasing. So since f is bounded and f is monotonic increasing on this interval -1 to 1, so we have the second theorem. If f is bounded and monotonic increasing, then it is integrable. So f of x is integrable. So f of x is integrable on closed f on -1 to 1. This is integrable on -1 to 1. So you can use this line, or you can say here the values of f of x, these things are 1 half 1 by 2 square. Similarly, if you write the nth term, this will be 1 by 2 to the power n minus 1. So if I write the nth term, what will be this one? This is 1 by 2 to the power n minus 1 when x lies between 1 by 2 to the power n minus 2 to 1 by 2 to the power n minus 1. So when x lies between this thing, so this is its functional value. So if we will check the points of discontinuity, so if we will check for the points of discontinuities, we will get 1 by 2, and then 1 by 2 square, 1 by 2 cube, dot 1 by 2 to the power n minus 1, dot these things, whatever the functional value you are getting. So these are the points of discontinuity. Or you can say this 1, then half, then 1 by 2 square, 1 by 2 cube. These are the points where the functional value changes. So these are the points of discontinuities. That means it has infinite number of discontinuities. That means it has infinite points of discontinuities. So since it has infinite points of discontinuities, and in the last point we said that if it has infinite points of discontinuity, then it should have a finite limit point. So if I will find the limit point, so limit n goes to infinity, so what will be your an? Suppose suppose I will say this is my sequence an, which contains infinite elements, and these are the infinite points of discontinuity. So if you will take the limit of an, then this is limit n tends to infinity. This is your term a1, this is a2, this is a3, this is your an minus 1. Similarly, this is your an term, this is your a1, a2, a3, then this is your an term. So limit n goes to infinity, an means limit n goes to infinity 2 to the power n minus 1. So in place of n, if I will put infinity, then 1 by infinity, this is 0. So this is the sets of, but this is the collection of points where, this is the collection of points where f is or f attains discontinuities, or where f is discontinuous, and these are the infinite number of points. So if you will find its limit point, this limit point is 0, which is a finite quantity. So we can say f is integrable and closed. F is integrable on this -1 to 1. Okay, that means if f has infinite number of discontinuities, and suppose you will say that is the set S, and if you are able to find the limit of that set, and if it is finite, then you can say your f is integrable. Okay, today is only this much.